Okay, very good. So today, your hosts are Alexis and myself. So Alexis is the founder and CEO of Hiphen, and I'm the R&D director at Hiphen. So we will be talking about plant senescence and how to best model plant senescence using UAV data. So the work we are presenting today is basically the fruit of the R&D project we conducted in the context of the Sunrise research program, which is a French research program in which the 11 partners are basically looking for ways to improve sunflower yield stability in changing environments. So we thank you for your support, and we thank especially INRAE, for which we've been conducting these plant measurements and projects. So thank you very much for allowing us to present all of that. So the webinar today is divided in 5 sections. So we will talk about plant senescence to start with. What is it and why is it important? We'll talk about UAVs and the equipment that we used for this use case. We'll talk about methods, how to best model it, and Cloverfield, which is our data platform that allows us to automate this kind of calculation. So the final part will be looking at the Q&A. And this is where we'll answer your questions in the chat bar. So do not hesitate to ask and type your questions in the chat as we go through the presentation. So a few words before we dive in. The Hiphen, as you know, is an expert in plant diagnosis. One of the key specificity of Hiphen is that we offer a wide range of traits. So we look at plants from like different angles, and we try to develop data pipelines that allow us to really characterize the plants in different views and angles, and we have a traits catalog that is quite extensive. And today we will focus on this one particular trait here called senescence. So I'll pass on to Alexis, who is now going to talk to us about this particular trait.
So thank you, Joss. So maybe before starting really about use cases and all that, some few words about senescence. So what exactly is senescence? So senescence is the moment where you're having decay of leaf area because the plant is dying. And this basically, in this webinar, will focus on annual plants. The phenomenon of this type of senescence in biennial plants, such as sugar beet, carrots, potatoes, or perennial plants, such as grapes, etc., is a completely different dynamic. So senescence is really interesting for us in the sense that it's where you're having grain filling. It can be on wheat, it can be on sorghum, it can be on corn, it can be on sunflower, which we will speak as use case today. But really, all my talk will be focused on annual type of plants. And once we said that, well, the growth curve of a plant is always basically the same in annual crops. You're starting to have what we call the vegetative stage. Then you're having the reproductive stage. And in this reproductive stage, well, you're having all the moment where you're having the reproduction, so flowering and fecundation, etc. And then you're having senescence, that is actually grain filling phase. And this is this phase that interests us. And this is this phase we're going to try to see how we can monitor for UAV. So it's something that is actually, as we can see and as we try to illustrate in this image, quite feasible. It's quite feasible in the sense that you really see the decay of the plants. And this decay of a plant is often linked to remobilization of nitrogen and other both biochemical compounds from the leaves and from the hood plant to the grain that will assure a next generation of plants. And this phase is extremely important because it's prone to any kind of stress, at the same time biotic and abiotic stress, so diseases and drought or other types of stresses. And those stresses will accelerate senescence, and the grain filling will not happen well. So basically, you're already having your yield potential that is defined before, and we're not focusing on that. But achieving this yield potential is all the topic of senescence, and that's why we want to try to follow it. In order to be able to assess the moment where you're having senescence, normally, well, you should be able to detect the moment where flowering and fecundation have been done. This is being done generally with IoTs or connected sensors in the field that are able to take 1 images every day. We have published through Cavia very recently a paper on that topic, and we welcome you to read it. And we can, of course, send it to you if you want. It's today in open access for the next 40 days. We also looked at it, and we could be able to follow this flowering phase, so this heading phase especially, through height dynamics. So we did that with LiDAR on phenobiles and with UAV. UAV were not quite precise enough to have the exact moment where height stops. So you first have a plant grows because of cells multiplications and then of cells elongation. So cells multiplication stops when you're having your grains that are done. In corn, it's going to be tassels. In wheat, here, it's going to be the head, etc. But then you still can have multiplication of elongation, of the cells that will continue growth. And generally, elongation stops when the grains are fecundated. And so basically when senescence starts. And so this is something that we try to do with phenobiles through LiDAR. We also have a paper here, and you're very welcome to come and read it as well. And finally, I do believe that it's very important for you to have ideas well set when we're speaking about stay green features. So stay green features, I think, is what all of you have already been following. It's one date where I measure my plants or with my eyes or with a drone or with whatever, generally NDVI, and I assess the amount of the greenness of my plants. So the capacity of my plant to continue to fix CO2, so to intercept light and to fix CO2 into biomass. And this is often a very important feature to understand if you're still managing to make grain filling or not. So it's a feature that breeders are quite eager to have in their crops. But this stay green feature is maybe not all what you need to describe senescence for many reasons. And for me, the main reason I see is because senescence will first start with biochemical compounds such as nitrogen remobilization from the leaves to the grain, but the plant will try to keep its photosynthetic system active as long as possible to be able to fix more CO2 and to fix more biomass. So generally, what I've seen during my PhD is that you're having nitrogen remobilization, so lost a little bit of the greenness of your leaves because nitrogen is linked to rubisco, which is tightly linked to chlorophyll. So decoloration of your leaves by maintaining intact the CO2 capability of fixing until the leaves dies. So this is in wheat more or less 100 to 115 degree days. And so you can follow it in different ways. You can follow the greenness and so the chlorophyll contents to follow up senescence. You can follow LAI, so the quantity of leaves you're having, or F-cover, the amount of leaves that are able to intercept directly light. Those are the main parameters that you can follow, and that are quite complementary. So once we said that, how do I do to follow the senescence the best? Well, the best to do is using crop models, very complex things. Why? Because we're able to integrate all those phenomena I described. I have never seen applications that really works in the real world for breeders using crop models today, maybe some with Epsin, but very specific. We can also think of curve fitting. We'll discuss that today. We can also think of area under curves. We'll also show some concrete examples today, or a single point, which is stay green features, which I think most of you guys already do. Please don't hesitate to ask questions on this a little bit vertical part about what is senescence. You can ask them now. I will go straight onto the use case. So the use case is the one we did on sunflower with INRAE this year. And so basically, they put some genetics. They put some genetics in the fields, 135 microplots. And they already had genomic modeling for senescence of those genetics that were achieved on another experiment with visual scoring by following up leaves. They made 11 flights from emergence to full senescence, to the plant dying. And there were some monitoring with RGB camera at the beginning and multispectral camera at the end. We will just speak about multispectral monitoring today. Please note two things. In 2020, we will only do RGB cameras, so we are able to follow up senescence for RGB camera as well. Here and that multispectral camera today we use Hiphen system, which is was a Hiphen product, but we would be able to do similar types of jobs with other multispectral cameras such as senescence or others. So this is not a limitation. So basically what we tried to do is we were trying to compare different types of models. So the quite modelization from cuts, that is basically as we describe it here. So you have a paper referring to it. Basically, you're having a logistic model that simulates the growth and another exponential model that simulates the decay of the plants, of the leaf area index of the plants. In our case, we just had VF cover, so we tried to apply it as well for VF cover. It does have some limitation because F cover saturates compared to LA, which can explain some of the bad results we had with this method. But I think it's the most physical way to try to model it for what we're going to present today. Then you have the bilinear approach. So it's something that I did a lot during my PhD, and so we published that in 2012, where basically you try to fit curves for the different phases as I described it you. So for this growth plateau, and then for the senescence. And finally, the last, and so yeah, and at this stage, we try to apply it either on all the data, but there maybe we should have used a trilinear model. And anyway, it's not that easy, as we can see when we focus on the plateau and then on the senescence. Well, you are having two phases of senescence. So then we have removed the late senescence, where actually the plant is already almost yellow. And then you have quite nice curves. It's never very fully satisfactory, those things, because we take and we remove points. So we do the same for all the microplots, but it's a little bit always handcraft. So one way to do it, maybe a little bit more robustly, is to take the area under the curves. So this was a paper that was already published in '77, comparing this type of fitting models or area under curves, and concluding that area under curves was much more robust, which also we agree. And in order to have something that correlates more with our perception of senescence, well, we normalized it, and then we took the area above the curve to be having something that increases when the plant is more senescence lower. And then we compared our measurements that you will see, and we will show you the curves just after that. So we compared our measurements to correlation with their genomic models of INRAE. And what we saw is that we had some quite neat correlations. And the best correlation we have was with the area under curves. So quite fitting with what our elders taught us in '77, with a correlation, so an R of 0.53, which made them quite happy for first stage work. I will let just now show you a little bit the curves of F cover we got. So this F cover we had was through pro-sales inversions, and how basically it looks like.
Yeah, thank you, Alexis. So here we can see some of the results. So we can see here all of the microplots plotted here for each flight we've done. So you can see the entire plant cycle. Here we are looking at F cover. So what we've done once we get to that stage is then try to sort the microplots to isolate some specific behaviors. And to start with that, then we isolate the senescence period. So this is how what we've done as a second step is focus on this senescence period. And from that point onwards, we normalized it. So here you're looking at a normalized AF cover for this period that then allow us to look at the speed of senescence, which is very interesting for us to then inspect the microplots and isolate the different behaviors. So here you can see 3 microplots, 3 extremes, basically. And if we look at the underlying images for these 3, you can clearly see the one on the right, which is basically following a much different pattern than the other one. So here is one way to sort the microplots based on all of this data, and this is a pretty powerful and robust way to model senescence and quickly inspect the microplots and assess the breeding trial. All of that is a data pipeline that is part of what we call Cloverfield, our secured online data platform. So this is a platform from which you can inspect the microplots individually and see your statistics and analytics as well. This is a platform that processes millions of microplots each year across the world. And with that, I guess the important message for us today as well is to make sure that you understand that at Hiphen, we really care about 3 important things. One is to develop the state-of-the-art technology and methodology that would not really allow us to be bulletproof. So for us, this is important because we really try to make sure that the pipeline can adapt to different field conditions. So this is an important thing for us. We really care about you being part of the work of the methods we apply. So you shouldn't feel like it's a black box thing that, as we hear sometimes from other suppliers. So we really want to make sure that you're engaged with method and that we are as transparent as we can. And we hope that today with this knowledge sharing session, you really got that point across. And finally, allowing you to scale is for us a mission. So we really want to make sure that you can scale across all your trials and territories efficiently. So now that's all great. Why should I care? Can I apply that solution to my experiment? We believe that the answer is yes, on all the annual plants, obviously. So we can look beyond the sunflower, obviously. And just to remind you, this is the catalog of traits that we offer at Hiphen, and we would be delighted to talk about how we can apply some of these traits or any other new traits that you're interested on your particular crop and experiment. So this is really the bread and butter of Hiphen in a way, and we offer very competitive pricing. I cannot leave you without that message, obviously, and we'd be delighted to look at your data. So if you have a sample data set that we could play with, we'd be happy to test it for free and send you a tailored proposal and take it from there. So by all means, do get in touch. Before we move on to Q&A, a quick reminder that next Thursday we will be talking about wheat and how to improve wheat spike counting. We have a guest, Etienne David from Arvalis, who is going to talk to us about his global wheat challenge, which is a very exciting initiative to improve these traits, so wheat spike counting next Thursday. So if you haven't registered, by all means, you can find the registration link on our website or on social networks. So without further ado, we can move on to Q&A.
So today we have 2 questions. Alexis Carlier is asking us if we tested other vegetation indices like PSRI. So the answer is yes, we tested all the type of vegetation indices. We tested all the types of method in this case. What we noticed is the big deal we're having is normalization. So how do you normalize your vegetations from the top to the end? And this often depends on the architecture. So the bottom line of a plant, of a type of cultivars in sunflower will not have the same bottom line depending of an indices, depending on its architecture. So, it will not be exactly the same yellow. It will not interact with light exactly the same way. So it's really hard to normalize vegetation indices, and F-cover was much easier to normalize, so to be able to have consistent area under curves. So that's why vegetation indices are actually very good, and I think quite powerful to try to monitor and to rank as stay green. So for one measurement, when you try to combine different measurements with different cultivars, it's always a little bit more tricky. So that was question one. Question two is Mr. Marandel that is asking the correlation between genomic and phenotypic senescence. So I believe it was I believe you're speaking about the figures we showed here. So that's the correlation between the phenotypic senescence we measured for drones and between the genomic senescence. If your question is a little bit different, please don't hesitate to write us an email or through LinkedIn, and I will be very happy to try to understand a little bit further your question and to answer it, or ask help from my colleagues from INRAE. Voilà. So I think that's the only questions we had today. Do we have other questions? So another question, have you tried deep learning to model senescence? So the answer is no, because it doesn't make sense. Why doesn't make sense in my point of view is deep learning is just a method to extract features from images. So we're going, I think in 2 weeks, we're having a webinar using as well some sunflower data where we'll explain you how we're making some plant-to-plant phenotyping, and to be able to follow also the senescence plant to plant, like the growth, like the flower head, etc. And there, of course, using deep learning is extremely useful to be able to extract those features. For senescence, it's basically the loss of green fraction. So you can compute F-cover using deep learning algorithm, but you also can compute it with other ways. In this case, we made an inversion of process modeling, but it could have been deep learning models. So I don't think it made much sense for a following up of senescence to use a deep learning algorithm. It does make sense to use machine learning, however, and I hope I answered to your questions. Another question we're having here is Sayan that is asking if a plant has drought tolerance, can we say that there is correlation between drought tolerance and F-cover? Yeah, that's a tricky question. Drought tolerance is a very blur question. Drought tolerance, if I try to give me a definition, would be a plant that is able to maintain high yield in conditions with little water. So is it with little water for the full cycle, or is it some drought events, so some events where you're having very little water at one stage and then you're having a lot later on? There we really focus on F-cover, so on senescence. So I think that drought deserves a full webinar to discuss about all the drought strategies and all the drought tolerance strategies for plants. Basically, I do believe that the stay green features are that when you're having an area above curve that is high, it means that your photosynthetic system is still viable, which means that probably you're more resistant to droughts. I hope that answers your question. This can be validated then by looking at yield. Yeah, it's more complex, and we will need a little bit more modeling with weather balance models, etc., to try to understand all those features. But yes, I do believe that using F-cover to be able to understand the dynamics of a plant for drought is interesting, knowing that more you're having F-cover, more you will evapotranspirate. So if you're having limited drought, you want a plant that is able to continue making light, intercepting light, and making biomass, using water for that as much as possible. And when you're having too severe drought, well, you want to limit the F cover to be able to have a plant that keeps the little water available and to close its tomates, etc. Yeah, it's linked, but not completely. I hope that answers your question. But someone has more question. Well, we're very proud to tell you that this webinar lasted exactly 26 minutes. I hope you learned things. I hope it was interesting for you. Once again, next week, we'll speak about a deep learning challenge about counting ears, heads in wheat, and that's really, really interesting. And if you want to participate, please do. And then we will follow up on another webinar on plant to plant, so trying not to make phenotyping for microplots, but really plant by plant. Thank you very much, and have a nice